Hello, everyone, and thank you for attending today's webinar, 5G Service Velocity and Distributed Service Provider Cloud, sponsored by Affirmed Networks and Juniper Networks. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green resource list widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day at the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading's Principal Analyst, Gabriel Brown. Gabe?
Thank you, Caitlin, and hello everybody. Welcome once again to 5G Service Velocity in the Distributed Cloud. Thank you all for joining today and for your participation. We hope you find the session useful and informative. Driven by performance and scalability demand, service provider networks are on the verge of significant and lasting change as operators start to re-architect their networks to meet advanced 4G and 5G service requirements. And so in this webinar, we're going to discuss really the twin themes of what we could think of as software-driven service velocity, how to develop, deploy, and operate advanced services, and the distributed service provider cloud, why and how to deploy cloud infrastructure at edge locations, how to provide a connectivity fabric between users, services, and infrastructure. And that should become clear as we go through the session. These are very much kind of interrelated problems and opportunities. My name is Gabriel Brown. I'm Principal Analyst with Heavy Reading, where I lead our mobile network coverage. And I'm joined by 2 expert guest speakers today. First of all, I'd like to introduce Ron Parker, Chief Architect at Affirmed Networks. Welcome, Ron. Thanks for joining. Could you say a few words about your role and what you do at Affirmed?
Certainly. Thanks, Gabe. So as Gabe mentioned, I'm the Chief Architect at Affirmed Networks, and we're a provider of virtualized mobile packet core solutions, and we're very excited to talk about what we're doing in the 5G and the service velocity space.
Terrific, thanks. And we also have Phil Lamoureux from Juniper Networks, where he's Mobility Architect. Welcome, Phil. Could you also introduce yourself, please?
Sure, Gabe, and thanks. Hello, everybody. My responsibility at Juniper is to architect solutions for mobility service providers and converged network service providers around our offerings of routing, switching, security, and of course cloud SDN based on our Contrail software. I'm very happy to be here today, and I love working with Ron and Gabe. This is a great team to work with.
Okay, good stuff. So I'm going to head on in just a moment with a short introduction before handing over. What I want to say is, as we do have some time at the end reserved for audience questions, but I've kind of established with both Ron and Phil, they're very open to taking questions. And actually, if we get some good ones, we can perhaps work some in during the flow of the presentation or at the various section breaks and such like. So I'd really encourage you to take advantage of their expertise. I know both speakers here are kind of deeply involved in the issues we're talking about. And if you think about it, this is more of a skim or a summary of their knowledge. So do take advantage of that would be my advice. So I'm just going to start by outlining a little bit really the sheer amount of activity underway globally by operators to develop and commercialize 5G technology. In every major region now, there are significant trials and pilots underway. I've highlighted some in bright red here, where you're looking at 2018 launches. The US market in particular is very aggressive on timing. I think all the big 4 mobile carriers now have said they're going to launch something in 2018. What's really interesting here is you have operators committing in low, mid, and high band, so the full ecosystem, if you like, from that perspective in one national market. We have lots happening in Europe. Communication strategy is a little different there, but there are extensive trials this year I think we'll see citywide launches in 2019, full commercial from around about 2020. Focus in Europe is more so on the mid-band and low-band 700 megahertz. I would say, in fact, I was at Orange in Paris last week where they announced their 5G trial program focusing on those areas and a few other things in millimeter wave as well. Asia is similarly very active. The Winter Olympics in Korea, South Korea, which is ongoing now, has just sort of long been earmarked as an opportunity to showcase pre-commercial 5G technologies. There's a big focus on C-band in China, I think looking at 2019 for that to sort of start rolling out at scale. And then, of course, you have places, Japan particularly, and Docomo is probably the sort of the bellwether I'd use in terms of a timeline aiming for a full commercial service by the Summer Olympics in 2020. So very exciting, lots happening. And I think a really key point here is these trial programs are not they're not really vanity projects, if you see what I mean. They're really, really important to how an operator thinks about, when they actually want to make the big investment in deployment. Your experience from trials is very critical to your CapEx efficiency, essentially. So if you want to be a progressive operator, you have to be doing this kind of trial work now to be efficient in your CapEx deployment and actually to have the operational processes in place to support that commercial rollout. So the timeline for launch is a little bit of a movable feast depending on your definition. I talked about 2018 earlier. We get quite a good sense in this quote from the new CTO at SK Telecom, also in South Korea, an interview he gave with Light Reading a few weeks ago, and talked about a timeline for smartphone modems following freeze of standardization, the first freeze of standardization for new radio in December 2017. It all comes together, really. We're looking at mid-2019, second half of 19 for, if you like, commercial handset type services. You can plot this on a timeline of sorts. I think this represents a pretty ambitious schedule, if not the most ambitious in the market. You have a number of operators have said now they expect to have citywide coverage in early markets in 2019. I think that's in all the major regions I talked about. But for me, we're still really talking about, and if you think back to that handset point and device UE point earlier, we're still really talking about 2020 for what you might think of as a launch of sort of mass market services where anyone can click an order or go into the store or whatever. The Summer Olympics in Tokyo has long been the sort of reference point for me. I think that remains so, even if we'll see some activity sooner at perhaps a little more limited scale. Note also there's an enormous opportunity for 4G over this period, and I think you could think about if you think about the term the 5G era, as some people use, that could definitely be said to include advanced 4G as well. We're really looking at an integrated 4G, 5G play for at least the foreseeable future. In terms of services for 5G, we don't know exactly which services will succeed and which ones operators will offer. That's kind of the point of a platform. But we do have a pretty good idea now of the types of services 5G will enable. Lots of work's gone on in ITU, in 3GPP, and in industry to identify some use cases and then determine associated performance requirements. I have a selection here. The main point is showing them really is just the diversity. So you could think of high voltage electrical grid distribution monitoring system, for example. You'd only need 10 megabits per second of user throughput, but you do want a consistent 5 millisecond latency, very low jitter, high survivability. Robotic motion controls at the bottom right here, you will have a millisecond of latency for one-way latency for the overall process. That equates to just 300 microseconds of network delay budget. So really, you're probably talking there about a local area deployment. If you talk about autonomous and connected cars, you have some various performance requirements, but also you want to really map that to a roadside coverage area type metric, same if it's rail or so forth. And in all these cases shown here, and more actually, there is a benefit, and I think practically speaking, probably a requirement to deploying network functions, application logic and services, and content itself in the edge cloud location. So I've done a very quick mapping here of some of these services to cloud location types, the robotic control system to the bottom right here, very low latency but throughput not so much, versus 8K video to the top left. Things like augmented reality and virtual reality, perhaps machine vision are sort of veering towards to the right, with tactile internet services right at the top right corner. It's just a representation, of course, not exactly scientific, but it shows, I think, how important edge cloud will be actually as part of a unified network cloud. You could also, in fact, map some of the network functions to this as well, 5G core, 5G RAN, and so forth. I also wanted to comment, just before I hand over to Ron at Affirmed Networks, that it looks like quite a lot of the opportunities for, if you like, a differentiated 5G network service will actually be in the enterprise market, whereas, you know, the 4G market has been very consumer-dominated and consumer-led, I think, albeit widely used in enterprise. We're seeing a bit of a swing back in 5G. Consumer remains very important. It's the largest slice, of course, but the role of different enterprise, different verticals becomes a lot more important. So even if you think of something like autonomous connected car, that service may actually come through the vehicle manufacturer or you know, whoever that may be within that value chain. So probably to keep in mind as we go through this, I think there are going to be a good amount of enterprise services that really drive some of the kind of key architecture decisions and actual network strategies. So with that, I'm going to hand over to Ron at Affirmed to take us through the next section. Ron, please.
Thank you, Gabe. So this presentation is service velocity in 5G, and you might think they're two different topics, but they're really related. 5G is not just a new radio. We're actually transforming the way we build these networks. So as we roll out our 5G networks, we're expecting far more than just better spectral efficiency over the air interface. We want to really monetize our networks to achieve this service velocity. So over the next 5 slides, I'm going to talk about the service agility, service velocity aspect of this. My colleague Phil will bring us through some use cases, and I'll come back at toward the end with a couple more 5G use cases tying it back to 5G. So what I'm going to talk about now, yes, it's 5G, but it's also very general to how we monetize these networks. So on this slide, we're showing on the right, there are a bunch of business needs. And on the left, there are a bunch of technology solutions to achieve these business needs. All of them are underpinned by service agility, linear scaling, resiliency, in short, cloud-native type of architectures brought back from the enterprise world into the VNF telco world. So if we start at the top here, we want to enter new markets, deliver customized services, and we do this through network slicing. Slicing gives us the ability to isolate one delivery vehicle from the next in order to introduce new things, fail-fast methodologies without jeopardizing all your existing services. So network slicing gives you this kind of isolation that lends itself to a very agile service rollout approach. We need to understand the customer and service experience, and here it's very important that everything be integrated with instrumented probing. So at Affirmed, we have vProbe technology that is part of every VNF that we build and deliver. So this leads to very rich data analysis, the real-time analytics, and closed-loop action. So this becomes a very important part of network evolution. We need to, again, rapidly deliver new services and capabilities. So the way we build it is through a microservices-based cloud-native architecture, and the way we roll it out is through service automation and slicing. Collaboration with third parties through to increase the innovation chain, so the innovations can come from the independent software vendor like an Affirmed Networks, can come from our customers, carriers across the world, or third parties. And how do you do that in practice? So if the entire architecture is underpinned by RESTful APIs over HTTP, this now allows third-party microservices to be introduced into the mix to further the innovation capability. And then lastly, reducing the cost of delivering this service, linear scaling, resiliency. So here we get to a web-scale microservices-based architecture. So this slide really matches the business needs of the technology solutions. Now that we've talked about that, what are the characteristics of the solution that achieves those goals? So at the top here, fine-grained network slicing is paramount to achieving the service velocity. That's your rollout vehicle. Integrated virtual probes, real-time intelligence, so you can see what's happening. You can act on it in a closed-loop fashion. Customized policies, DPI, GI-LAN value-added services, service function chaining, all come into this over an NEG architecture. So as we build out this new common core, it should be able to absorb fixed wireless, Wi-Fi, any of the legacy access techniques. It needs to be high performance, so the solution is built around a CUPS architecture, which is control user plane separation. So now we can deploy separate network elements for the control plane and for the user plane, and we can physically separate them when we choose. We can have many-to-many topologies of controllers to user plane instances across the network. All of this requires automated service provisioning. The more stuff you have out in the network, the more actions you're taking on the network, the more important it gets that you have a high degree of automation. This also plays into a network that's optimized for IoT, because as we go forward, the count of devices is increasing rapidly. If we had tens of millions of smartphones on our network, we can have hundreds of millions to billions of smart devices on our network. So we need networks that are scaled this way, so our solutions have to account for that and do. And then lastly, a microservices-based architecture with HTTP RESTful APIs. All this together lead to the continuous innovation you need for service agility. So this slide puts those two things together. How does a microservices cloud-native architecture and slicing come together? What's the connection there? Well, very simply, a microservices-based architecture allows the vendor and the vendor's partners to rapidly innovate. Now, instead of large monolithic software releases that roll out maybe once or twice a year, we have independent microservice releases that can roll out in 2 to 4 week time frames. And that gives you tremendous agility in terms of producing the software, but how do you use the software? How do you deploy the software? So this is where slicing comes in. So some of these vehicles here are loaded with multiple microservices, and the depiction is that you're rolling out new types of slices, new instances of slices to hit specific verticals or even specific customer instances. And this happens frequently and requires a high degree of customization. So the finer grain you get on slicing, the more likely it is you need some software feature to adequately satisfy that kind of slice, and you need fast turn on that. So that's your connection between microservices-based architecture and slicing. The one of them allows you to produce the new software features very rapidly and validate the new software features very rapidly. And the slicing allows you to deploy them in an isolated sandbox without risking already deployed slices. So we think this is a real marriage of these technologies, and we can even extend this into a DevOps type of view where in DevOps you're developing rapidly, you're validating rapidly, and you're deploying rapidly, you're monitoring your deployments, you're rolling back when necessary, you're going forward with scale when it's necessary. So we think these two things are absolutely tied together, and we think that any kind of 5G agile network must be built off of a microservices architecture to achieve these benefits. So an example of this kind of slicing, it sorts into the 3 pillars of 5G, which is enhanced mobile broadband, massive IoT, and low latency communication, or ultra reliable low latency communication. So we can see slice examples in each of these, where for mobile broadband perhaps you have prepaid slice, postpaid slice, maybe you map your fixed wireless into this mobile broadband category. But it's not just a fixed wireless slice. It could be one for residential and one for small businesses and more for large businesses getting their own independent slices. And consumer MVNOs are certainly another category there. If you look at IoT, there's so many different examples. IoT is inherently an enterprise story. So here we could have isolated slices for federal government, different car manufacturers, farm conglomerates, mining, smart cities. So it's not just the category, but it's also the instance. And likewise, there are a lot of public safety as well as health and industrial automation examples for low latency. So I think what we're trying to show here is that if you want to get to fine-grained slicing, you need a small minimum cost of entry, which a microservices-based architecture gives you. So you can start very small and grow to any scale that you need, giving you cost-effective scaling. And you need the rapid feature delivery because the finer grained you get, the more customized it needs to be. And then the last slide in this section, before I turn it over, is just another dimension of this flexibility of microservices and microslices, that as you get finer and finer grained, it's not necessary that an individual slice have isolated everything. There are flexible degrees of sharing, and there's a hierarchy of slicing where perhaps the federal government wants isolated everything. So here I'm showing some of the 5G components, the AMF being the mobility management, SMF being session management, UPF being user plane. So let's say federal government wants distinct and isolated instances of everything for their slice. But the car manufacturer may be willing to save some money by having isolated session management and user plane, but maybe share the mobility management with the other car manufacturers and perhaps other enterprises as a cost-saving measure. And then maybe the farm conglomerate would like to have their own distinct user plane so they can do their own service function chaining, for example, but are more than happy to save some cost and share session management, application management. So this shows you that even with fine-grained slicing, it's not a requirement that it be 100% isolated. You can actually dial up the degree of isolation you want, and you can have a hierarchy of slice to shared slice. And with that, I would like to turn it over to my colleague, Phil.
Thanks, Ron. So one thing that should be obvious at this point is that with all of the ways that you can flexibly slice the network, there's many opportunities here for automation and for orchestration. And Ron mentioned the hierarchy, a hierarchical network, and that's what I'm going to talk about here to quite an extent. The need for, or the deployment of, a distributed cloud that will push functions closer to the edge, closer to the RAN. You need to consider that the real world networks are really frequently converged networks, operators that have wireline and wireless operations, meaning that they have a converged transport, converged locations. Think of the old central offices and MITSOs that really are prime real estate for deploying cloud locations. But many of those are converged. So we have to think about not just the virtual network functions, but the whole transport infrastructure and connectivity having to be under slicing control as well, right? So think of creating an end-to-end network slice where the network functions, the mobility management, the user plane anchoring, the transport of user plane and control plane, and all the nodes that are comprised, routers and switches that comprise the network, all really need to be sliced to maintain those requirements that Gabe mentioned earlier, right? Those service offerings for massive broadband or for massive IoT, right? Those service offerings all have unique requirements that need to be enforced end to end through the network, right? That's kind of a key feature here. So one of the elements that you'll take advantage of in building this kind of network is the programmability of the routing network. So having a programmable routing software, such as Junos, is of great advantage, because what you're going to do is close the loop from telemetry of monitoring those SLAs for each of those slice requirements, and then enforce changes or push changes that are needed to maintain those SLAs. That's a function of a wide area network SDN software. But you also, within each of the stacks, the cloud stacks, you'll have to enforce those same types of SLAs as well. So it's automation not just of routing nodes, but of the whole cloud infrastructure as well. It almost sounds like with all the telemetry that can be collected from each stack and from each layer of the stack, it sounds like this is prime need for automation. It's pretty complicated. You're going to need machine learning and an automated service provisioning, which Ron mentioned earlier that Affirmed brings vProbe. They also have an automated provisioning platform, and in Juniper's world, we've got a complementary product in the network slicing bot. You'll be hearing more about that over the next few weeks, where the needs of each slice are treated as policy and can be managed and maintained and pushed into the network to ensure that you're meeting the requirements. The other thing to consider is the security of links across different layers. I'll be talking about that on another slide. But one of the things I want to point out too here is that the various locations where that the cloud can be distributed, right, from very close to the edge hub sites or aggregation sites in the backhaul network, up through maybe slightly more regional sites, all the way up to highly centralized sites. There's going to be this hierarchy, which is going to exist in a much more prevalent than today's service provider network. In a sense, these distributed clouds look very much like multi-cloud. In the cloud native environment, we talk about having multi-clouds, clouds that are coordinated between private clouds, the public cloud services, and we're going to have this federation of clouds. And so security between the different cloud elements, or I should say the elements of a slice that exist in different parts of the multi-cloud, security of those layers is going to be absolutely essential. And so being able to encrypt the overlay tunnels, both in the forwarding plane and also in the control plane of each of those tunnels, is essential. And that's one of the advantages that Contrail brings to you. And being able for an operator to have visibility, a single pane of glass, to be able to manage the services, the endpoints of the services, regardless of where they end up. So you can think of that mobile cloud that you see in the center here may have endpoints that exist in an enterprise cloud, for example, vehicle manufacturers who want to run their telemetry services for smart cars. They'll want to run that from their own cloud, for example, but may need enforcement and some parts of the application to be running very close to the automobiles that would run on the mobile cloud. So it sort of opens up too an opportunity for hosted services as a service, or hosted applications as a service that the service providers can offer to enterprises and to consumers. You know, any of the groups that are listed in the slicing types. And then the next, the next point here is that you know, the way that security, the way that the clouds can be built, you know, we have a legacy of physical network functions, and you know, today we have network functions built on virtual machines. But coming soon, we've got microservice-based network functions, which will be containerized, and so having an SDN controller that can help build tunnels and integrate the services through both physical, virtual machine, and container-based network functions is absolutely essential. And again, that's one of the advantages of Contrail. In addition, the requirements needs of slices of all the different slice types kind of suggests that they may be different security requirements, which having something like a microservice-based firewall, or I'll call it a security appliance, that can be deployed, you know, at different points in the network to allow you know, the kinds of security that you may need for each different type of service. In addition, you want to be able to not just be constrained to one security services from one operator, or one vendor rather, but you may want to you may need to bring in say third-party security services, and again, having an open SDN virtualization topology gives you that ability to bring in third-party security. So if you think about, you know, where the workloads kind of extend, and the different combinations of workloads, you know, you've got a pretty complicated and varied environment. That again, the idea of using machine learning and automating the performance along each slice is a key point. And again, that's one of the items that you'll get using a network slicing bot that we're introducing. So Ron, let's talk about some use cases. You want to lead us through?
I would be happy to.
Yeah.
Great. So as promised, I was going to circle back to 5G use cases after we talked about all of that software agility and service velocity. So in the first, I have two, and in the first, this is a 5G capable UE. Let's call it a smartphone, if we will. It's going to be dual connectivity. So this is going to have LTE and 5G dual connectivity capability, and such devices are going to roll into the network incrementally. It won't be that on one day all devices are 4G and on the next day they're all 5G capable. So how do we handle that? So In traditional LT networks today, many are still using legacy physical EPC, which perhaps will not be able to handle the what we call the 5G non-standalone capability, which is the mating of 5G radio with a slightly enhanced EPC. So let's surmise that we'd like to direct our 5G capable UEs to a separate network overlay, and we can call this a slice. So we can say we'd like to create an EPC slice for our dual connectivity non-standalone 5G capable UEs. So this is a precursor before we get to a full next generation 5G core. We have this interim where we can marry the radio with the EPC technology. But we'd still like to stand that up as a virtualized EPC because it has the characteristics we want and has the software agility we get through virtualization and through cloud native architectures. So here we're showing a capability where you can insert a slice selection function, virtual slice selection function shown as VSSF, in between the MMEs, the pool of MMEs, and the gateways in order to do per UE steering selection of session assignment. So an MME can, via DNS, can do per APN, but presuming that the overhead to segregate your dual 4G, 5G UEs into a separate APN is really quite high for a variety of reasons. So we can keep those in the same APN and then pick them off as they come onto the network and assign the dual capable UEs to the new non-standalone EPC slice and allow the legacy UEs to continue to go to the legacy EPC. And now what that allows us is for these dual capability UEs, even when they're on 4G, they'll still be on the new slice. So they'll do inter-rat handovers between 4G, 5G, all the while on the next generation core. So now we get all the benefits of continuous analytics by the vProbe streams heading to the analytics analysis box. Gives you the opportunity to do any closed-loop optimizations you'd like to do, perhaps effected through a service automation platform like the Affirmed service automation platform shown at the bottom. So by diverting the new higher capable UEs to the new slice, you get all of these capabilities even before you've upgraded to a full 5G NG core. And then the next example and final example that's very interesting in certain parts of the world is 5G for fixed wireless. So again, here we probably have initially the non-standalone approach, which means that the home CPEs with outdoor antennas for 28 gigahertz, 34 gigahertz spectrum, 5G uplink, but still to a enhanced EPC core initially doing this non-standalone approach. So in this example, it lends itself really well to deploying the U-plane at the edge. So we have no mobility. The homes are not moving. The small businesses are not moving. So if we have a flexible IP services network where we can extend the internet edge, which in mobility we call the GI interface, if we can extend that out to edge aggregation points, it lends itself perfectly well to the fixed wireless type deployment. And now we can leverage also the control user plane separation architecture, where we deploy our user planes out at the edge, where we see that natural aggregation because we presume that the homes and small businesses are consuming far more data in total than smartphones would. So you want to get that aggregation further to the edge, but you have to be able to drive the internet edge out there. Otherwise, if you're just backhauling to a central site anyway, you haven't achieved very much. So you'd like to do a direct offload at that edge, where you've got your user plane network elements deployed as VMs or containers or a hybrid of containers and VMs. Likewise, you've got your control plane at the central site, but there's one more complexity. In general, a UE is going to join more than one APN, application provider network, and in this case, there would be one for internet and one for IMS, so the voice over IP calling can be realized. And that does not lend itself to edge aggregation. So this is another advantage of a CUPS-type architecture, where for that UE, we can host both the sessions on the same controller, shown here as centralized C-plane, and one of the sessions can be anchored at the edge U-plane, and the other of its sessions can be anchored at a centralized U-plane for handoff to the IMS, which tends to be more centralized. And all of this gets the benefit of this closed loop of continuous streaming of virtual probe data and analytics on that data in near real time, and the potential to do closed loop changes to your network, policies, or even slice creation through an automation platform. So we think these are two very good examples to tie all of that service velocity, service agility aspect into 5G, where we start with mobile smartphone type service as well as fixed wireless service. Both of them lend themselves to that service agility and slicing capability. And with that,
yeah, just I add something here. This is an example. Whoop, can you go back? There we go. Thanks. This is an example where the multi-cloud type environment comes into play. I mean, shown here, you have ostensibly two clouds, right? An edge cloud and a centralized cloud. That's the domain of the mobile service provider. And the data path that Ron described is offloaded out to the internet as quickly as you can, right? But you can also envision a situation where this home is also a home office with the user that has to interact with applications that are running in their enterprise cloud, right? So there can be yet a third data path that's in a secure tunnel to the enterprise cloud, right? Or the enterprise could host applications if it's a high bandwidth type or low latency type application. That those applications could be hosted in that distributed edge office, as shown. So this is a great example, in my view, of how the interactions between the different layers need to be coordinated and automated and synchronized, right? So that we can meet the SLA type conditions, the requirements for each of the different end services and applications that are being used. Thanks, Ron.
Yeah, and thanks, Phil. And I think with that, we've wrapped up our examples, and I'm going to turn it over to Gabe.
Okay, thanks, guys. We have a very short conclusion here that I won't even actually go through, more to bookend the presentation. You can download these slides actually off the tool itself. What I'd like to do is jump in direct to Q&A. We have some good questions already in, and still plenty of time if you have a question. I'm actually going to go to Phil first. Ron, if you want to contribute after, feel free. Question here, Phil. What is the typical deployment footprint of the 5G service-based core? Is it office building, office park, municipality, metro area? Could you maybe put a bit of color on that?
Sure. And I think the short answer is it depends on the services and the requirements of those services that you want to offer. So all of the scenarios from office park to a residential neighborhood to maybe just several city blocks in a dense urban environment, all the way up to a small town, or those are all viable options, right, or viable deployment scenarios. It really will depend, and this is the beauty of virtualization, right, is do you have room for servers? If you have a place that you can run servers, you can drop in a core. And an application cloud environment for, along the lines of mobile edge computing, right? That's, it's a highly flexible. So what's really going to drive the answer here is looking at the cost for deployment, for real estate, for power, and that I think will drive a lot of these decisions.
Yeah, good point. Ron, any comments on that?
Yeah, I'll just add that in a cloud-native architecture, the minimum footprint is small. So the minimum cost of entry to stand up a core, and that could be part of a core too. We can separate the MME part, we can separate the gateway control, the gateway user, or the 5G equivalent pieces. So minimum cost of entry is small, so it gives you a lot of flexibility to deploy what you need where you need it. And automation helps tame the tyranny of numbers that might result by doing this kind of very fine-grained slicing.
And perhaps either of you, Ron first in this case, and Phil, if you like, do you have any sense as to, obviously we have a lot of flexibility available, but do you have any sense as to the numbers of edge locations operators may use? And candidly, I hear a very wide range from thousands to tens, if that makes sense. Obviously, there's a lot of different operators in the world, but do you have a feel for what they're likely to go with?
Yeah, so I think when you talk about tens of thousands, especially in North America, this tends to be eNode B sites, where a carrier might have 80,000, 100,000 eNode B sites. And I know a lot of the mobile edge computing talks about putting user planes there. It's a very costly place to deploy and manage, and the numbers get real big real fast. Servicing those sites is particularly difficult. So theoretically, you could deploy at the eNode B, but I think that many edge applications will be more than happy running at the first aggregation point. So, wherever it depends on your topology. If you're backhauling point to point with fiber from your eNode Bs, or you've got some sort of metro ring type topology, that first aggregation point, perhaps the head end of the ring or the natural point-to-point aggregation is a more logical place, in my opinion, to deploy those kind of edge services that want the absolute lowest possible latency. I think the backhaul between the eNode B and that first aggregation point doesn't add enough additional latency to really to obviate the solution.
Yeah, I completely agree with Ron, and the way that we've looked at this problem is by working from the base station in. So as Ron pointed out, the first aggregation node aggregates, obviously this depends on the network, but could be, say, 50 to 100 to maybe 200 sites, but 50 to 100 is kind of the sweet spot. That's whenever we've looked at the economy of building out a cloud, that seems like it's the first viable hop. Right? It has the 50 to 100 eNode Bs. And then, in kind of typical, when you go from, say, the first hub site or aggregation point up to larger aggregation, you have maybe a factor of 10 to 20, right? So maybe now you've got as many as 1,000 eNode Bs that you're aggregating. There may be places where where it makes sense to deploy a cloud there. It's certainly feasible. Having a federation between the clouds, the one that's very close to the eNode Bs and the one that's maybe 1 or 2 hops up, is essential if you're going to say you maybe use that as a geographic redundancy site, or there's a lot of ways to play this, but maybe the way to think about it is 100 eNode Bs, 1,000 to 2,000 eNode Bs, and then you're up at the several thousands to 10,000 eNode Bs.
Good stuff. I think as you talk about these number and types of locations, what I thought was quite interesting in both your materials is how you talked about as it were, the monitoring and probing type functions. I was talking this through with quite a large operator here in Europe a month or two ago. Could very much see the case for distributed core and all this kind of thing, but their issue was, well, we have about 3 locations per country today, and each of those locations is fully instrumented. So as soon as we start moving, gateways out to the edge, things like that, we've got to also replicate all that instrumentation. It sounds like you thought of that because you both mentioned it, but could you just elaborate on that issue specifically? Because it turns out to be quite substantial, certainly operationally for carriers. Ron, I guess I'll go to you first on that one. Or Phil. Phil, you start.
Okay. I'm sorry. So, yeah, with respect to instrumentation, I think you're really referring to analytics in this case?
Yeah, performance monitoring, analytics.
Yes, absolutely. So, we continue to have the traditional performance monitoring, bulk statistics, KPI, thresholding, that kind of thing. But I think, the limitation there is it's whatever we preconceived was the interesting or correlated data that needed to be counted, tracked, thresholded. And I think where a big data approach comes in is it means you didn't have to get all that right up front, that by streaming a lot of low-level data that, like we stream at the 5-tuple level, for example, every single 5-tuple gets at least 1 record, but long-lived flows get more than 1 record. And the record is all pre-correlated back to the subscriber data. So that's why we call it a vProbe, that it's all pre-correlated, it's very efficient, and it can be ingested by a variety of analytic systems. So I think accounting for the bandwidth necessary to stream all of this real-time data off the deployed solutions if they're at the edge, you do have to account for the backhaul of that data as well. I mean, it's not nearly as large as the actual user plane. That's the point. It's, describing the flow is different than copying the flow. It's far, far more efficient. But nonetheless, there's a significant stream of data, and you might end up needing a very large ingest and analytics system, which will tend to be more centralized as a result of that. So I don't think you necessarily complicate the edge topology because you have rich analytics. If merely you account for the backhaul bandwidth of those streaming records, I think then the complexity still resides more in the centralized data center where you deploy the big data system.
Yeah, there's no way that I would underestimate the work involved in deploying telemetry and monitoring the telemetry and then automating the response, right? I mean, in the limit where you want to get to is what in Juniper we've referred to as the self-driving network, where you understand the telemetry needs well enough. The system, the software-defined network system, is monitoring the telemetry and has learned how to, so through machine learning, to take the appropriate actions necessary, and so the maintenance folks don't get phone calls in the middle of the night. When they come in the morning, they get a report. Here's what we did overnight to make sure that all the service SLAs are being met. That's the goal, right? And we're taking steps to get there. One of the steps is Affirmed. You saw it appear on some of the slides. But Affirmed deploys a small, very lightweight client on each of the hosts, each of the servers in the virtualization environment, both ones that are running VMs, ones that are running containers, and is monitoring the health and performance of each of those nodes down to the VM or container level. and then is in an intelligent way massaging and maintaining that information to be predictive about the health of that host and the environment that those VMs are in. So it's not only the host; it's also the interfaces and that sort of thing. But that's a step along the way to having this completely self-driving network that simplifies the amount of monitoring that you have to do.
Yeah, okay, good stuff. So I'm going to move on to a couple of other questions here. Ron, for you in the first instance, how do you coordinate the telco load, for example, the virtual EPC running on a server in the edge data center with the IT load, for example, other MEC applications in the edge data center? How do you coordinate that in the NSLCM? I think that means Network Service Lifecycle Management process, especially in the presence of mobility of the user sessions. So I think that's getting at how you coordinate load on, essentially load on the infrastructure in the presence of mobility.
Yeah, this is a complicated question, and I think it's a layered answer. So the network slice lifecycle management, I'm not sure how quickly we're going to get to dynamic slice creation. And slice creation is generally in response to a business need. So you've sold, as a carrier, you've sold a service to an enterprise, and through that negotiation, you determine the level of isolation that is required and appropriate for that enterprise. The slice now, in turn, is a collection of resources deployed in a collection of locations. So managing the footprint of the slice can be dynamic in terms of dynamic scale at a given location. Dynamic instantiation of a new location, perhaps you thought you needed a user plane at an additional small city that's close to an existing large city user plane. That could happen through closed loop automation for sure. But then that's a layered problem. So you've perhaps added a new location to your slice, but now you've got differing loads at the locations within the slice, and that brings in another question, which is MEC's question of how do you do mobility. So when you have MEC mobility, you've both perhaps changed the load in a particular location, because if perhaps a large quantity of users are leaving an arena, the load at that arena drops significantly and surrounding areas pick up significantly. But there's the other question of context. So the core network understands that the mobility context is being handed over from one site to another, from one eNode V to another, from one gateway to another. The core network understands that. But MEC also needs to do the application context. So MEC needs a view of the mobility context, and MEC also needs to worry about handover of the application context. So the MEC platform, if it's more tightly integrated with the EPC, or let's just say with EPC, will naturally have a view of the mobility context. But the application context, I'm a user, I'm using some service while I'm in the arena, and the application location is close by to the arena, and now I take the train and I'm closer to my home. I wanted to continue using that application, but I needed to shift it to a location closer to my home now that the train has gotten closer. How that happens is really application specific. So between the client application and the server, any context handover at that level has to be application specific. So the core network and the MEC platform can cooperate much more closely on mobility context. And in 5G, this becomes more natural yet, where we can have a hierarchy of user plane locations, really obviating the need for a MEC shim. In 5G, this gets easier. But it's really a layered answer around how context gets shifted, how load gets monitored, how dynamic scale happens, and perhaps closed loop control of the actual location footprint of the slice itself.
Okay, good stuff. So with that, we actually come to the top of the hour. We have several other questions we haven't quite got to, so I'll ask the speakers to review afterwards, and if they feel appropriate to get in touch with you via email. Thank you very much for those questions, by the way. With that, it just comes to thank Ron Parker from Affirmed Networks for being with us today. Thank you, Ron.
You're welcome very much. My pleasure.
And also to thank Phil Lamoureux from Juniper Networks. Thank you, Phil.
My pleasure, Gabe.
And finally, thanks to everybody in the audience for attending today. We certainly appreciate it. Thank you very much, and goodbye.